Hello, hello. Testing, testing. Good. Yeah, hey, just following on from yesterday, I think. Was it yesterday? Yeah, I think so. Episode 42. Very proud moment of mine. So, I think we got to this Graham-Schmidt theorem, and let's take a look at that. If I can find the right page, that is. Okay, and then I think, yeah, I can see them. The two special dots that align my screens. Alrighty, okay. Let's start. Graham-Schmidt theorem. Let us now take up the Graham-Schmidt procedure for converting a linearly independent basis into an orthonormal one. So linearly independent means that vectors inside a vector space must not be able to be added together to create a new vector, to create a vector that's also inside the vector space. A vector space is a set of vectors. An orthonormal means that the inner product of the vectors results in 0 and that the vectors are of length 1 or magnitude 1. The basic idea can be seen by a simple example. Imagine the two-dimensional space of arrows in a plane. Okay, let's imagine that. The two-dimensional space of arrows in a plane. Arrows here and here. Let us take two non-parallel vectors which qualify as a basis. Which qualify as a basis. A basis is, oh dear goodness me, I always forget. It is a basis is. I know that the basis was that they are just the 1 0 0 0 1 0 0 0 1, but I can't quite remember precisely what that meant. What is a basis? What is a basis again in terms of orthonormal basis? Let's just get a quick reading of this. Basis. In linear algebra, a basis for a vector space is a set of vectors that spans the space and is linearly independent. This means any vector in the space can be expressed as a linear combination of the basis vectors. Any vector in the space can be expressed as a linear combination of the basis vectors. No vector in the basis can be expressed as a linear combination of the other basis vectors. I see. So to remind ourselves, it's when the other vectors can create a basis in the vector space, but that the basis vectors themselves cannot create one of the other vectors. And we know the rest. Okay, cool. There might be some more to that, but that's enough. So to get an orthonormal basis out of these, we do the following. So it says, let us take two non-parallel vectors which qualify as a basis. So maybe we don't want to be drawing this because I wouldn't know how to draw them. Rescale the first by its own length so it becomes a unit vector. This will be the first basis vector. Subtract from the second vector its projection along the first, leaving behind only the part perpendicular to the first. Such a part will remain since by assumption the vectors are non-parallel. Rescale the leftover piece by its own length, We now have the second basis vector. It is orthogonal to the first and of unit length. This simple example tells the whole story behind this procedure, which will now be discussed in general terms in Dirac notation. So given that they haven't given me a graph, then maybe we should just try this. So it says um, two arrows. Let me just make sure this is muted. It is. And you can see it all. Good. Cool. Two non-parallel vectors which qualify as a basis. So if we remind ourselves again, it's when any vectors, two vectors can create a basis, but that the bases cannot create another vector. So I guess we can just say something like this, where this is v2, this is v1, and the projection onto that is going to be this. So here is the projection. Rescale the first by its own length, so it becomes a unit vector. Rescale it by its own length. I don't think I need to redraw that. Subtract from the second vector its projection along the first. Subtract the projection along the first. So get rid of this. Leaving behind only the part perpendicular to the first. Perpendicular. That's at right angles, isn't it? Yeah. Well, that's interesting, isn't it? Because subtract from the second vector its projection along the first. Ah. So we have to imagine that this is smaller. And so this will be the projection on the first. And so this gets scribbled out. Rescale the first by its own length, so it becomes a unit vector. This will be the first basis vector. Subtract from the second vector its projection along the first. Subtract from the second vector its projection along the first, leaving behind only the part perpendicular to the first. Well, I mean, it's not perpendicular, but okay. Such a part will remain since by assumption the vectors are non-parallel. Ah? Rescale the leftover piece by its own length. We now have the second basis vector. It is orthogonal to the first and of unit length. This part. Ah, I do get it. Let's see. Picture of Gram-Schmidt theorem. Ah, here we go. Thank goodness. I did click that. Nothing's happening. Now it is. So vector 1, vector 2. Vector 2 is cast onto 1. So I did do that right. And then this scaled by itself. Let's check this out.
Let's say I have a set of linearly independent vectors v1.
Here we go.
This is going to be a plane in Rn, so let's just make our chalkboard here, our video board here, the plane. So we have u1, which is a unit vector. It has length 1, so that is u1. And u1 and well v1 and v2 are linearly independent. That's by definition of a basis. So you can't represent v2 as a linear multiple or a linear combination of v1, and likewise you can't represent v2 as a linear combination of u1 because v1 is a linear combination of u1. So v1 is not going to be on the line spanned by u1. So I could actually draw that. The line spanned by u1 is just like this. This is the line spanned by u1. Let me draw it a little bit better than that. I don't want to make it too dark. That is the u1. So this is v1 right there to get to u1. So the span of v1 is the same as span of u1. That is this subspace. That's this line in Rn. Now we have vector v2, which is linearly independent from v1 and u1. So v2 would look, let's just say it looks something like that. v2. Now what we want to do is replace v2 with another vector that is definitely orthogonal to this, and we'll still be able to construct v2 with some combination of this and our new vector. Well, the most obvious vector would be some vector that is orthogonal to v1. So it's orthogonal, so it's a member of the orthogonal.
So let's read this again. It says, imagine the two-dimensional space of arrows in a plane. Let us take two non-parallel vectors which qualify as a basis. To get an orthonormal basis out of these, we do the following. Rescale the first by its own length, so it becomes a unit vector. This will be the first basis vector. Subtract from the second vector its projection along the first, leaving behind only the part perpendicular to the first. Such a part will remain since by assumption the vectors are non-parallel. Rescale the leftover piece by its own length. We now have the second basis vector. This simple example tells... I don't understand it. But it's fine. It's not clear anyway. Let ket I and ket II be a linearly independent basis. The first vector of the orthonormal basis will be is that an L or a 1? I mean, I actually can't tell. Let's try and zoom it in. Thanks, Amazon. I think that's that's a 1. So the vector basis of 1 is equal to I divided by the magnitude of I, where the magnitude of I is the square root of the inner product. Clearly, the inner dot product is equal to the inner dot product, no, the inner dot product of the basis vector, 1, is equal to the inner dot product divided by the magnitude squared, which is equal to 1. Let's try that then. So it says vector 1 is equal to I ket divided by the magnitude of I, where the magnitude of I is equal to the square root of the inner products of I. Okay, which is, I didn't mean to write that one. Oh well, let's just do this. So sorry, 1 inner product of 1's is equal to the inner product of the i's divided by the magnitude of I squared. which is equal to 1. Okay. I think what I'll do is I'll do this like with a line here like that. Yeah. So let's put some stuff in then. Let's say that 1 is equal to um 1 0 0, and uh, and that means that the inner product of 1 is equal to um, 1 times, well, let's just make it two-dimensional, right? 1 times uh, 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 0, which equals, which equals 1 plus 0 plus 0 plus 0, which equals 1. So we agree so far, but also then we have to do the inner dot product of I. So let's imagine I is equal to 2 plus I, yeah, and then the bra of that will be equal to 2 minus I, and then so the inner product of i's is going to be equal to 2 times 2 plus 2 times I plus I times 2 plus I times I, which equals 4 plus 2I plus 2I plus I squared, which equals 4 plus 4I minus 1, which equals 3 plus 4I. Okay, and then we want to divide it by the magnitude squared. So but I is linearly independent basis. The first vector of the orthonormal basis will be now how do you take the magnitude of I squared? Let's see, my browser is not responding. Oh, here we go. So given I, or is that 1 1? Oh, it's 1 1. No, no, we did that, yeah. 1, 1 equals I divided by I, power of 2 equals 1. So given I are linearly independent basis, the first vector of the orthonormal basis will be 1 equals I divided by I, where I equals the square root, I see it now, of I. So it's actually given it to us here. And then it says clearly well, we actually know the answer then, so it's going to be the square root of it. So the square root of I is going to be I is equal to square root of 3 plus 4I. And so let's first ask, I therefore decided to plug in some variables. I started with 1 equals 1, 0. Therefore, 1, 1 is equal to 1 times 1 plus 1 times 0 plus 0 times 1 plus 0 times 0, which equals 1 plus 0 plus 0 plus 0, which equals 1. And then I decided I is equal to 2 plus I. And that's interesting actually, because I actually probably do need to. Let's just do this. Let's just recap on this one because this clearly is a bit wrong. Because we'd need well, at least I meant to do two sets here, two sets of coordinates. So let's just do that to make life simple. Yeah. So then it would be 2 plus I times 2 minus I plus 2 plus I times 2 minus I plus 2 plus I times 2 minus I plus 2 plus I times 2 minus I, which equals 2 plus I times 2I is 4, and then it's minus 2i, and then it's plus I plus 2i, I times minus I times minus I. Is a minus, okay. Which would be minus I squared, and minus I squared is a minus minus equals a plus, so it would be, well, I squared is negative 1, right? So let's do, it's I squared is negative 1, and so I times minus I, oh wow, why is it I struggle with that? I times minus I equals 1. I times minus I. That's because it becomes minus 1. So I guess they're doing I times minus I is equal to 1, 1 minus I. So it's 1 times 1, 1 times 1 is, sorry, I'm really bad at this. Minus 1 I squared. We got to that point already. Minus I squared. And then it's, oh, is that all you have to do? Minus 1, because you got the 1 at the front, you do minus 1 times minus 1, which is 1. Okay, cool. So fine. That's fine, that's fine. Plus 1. So, that's going to be the same across the board. So you've got, let's just simplify this. 4 minus 1 is 3, and then minus 2i times 2i is minus 4i squared. It's going to be minus 4 times minus 1 is plus 4, which equals 7. So the inner product of I is 7, so the square root of that was it the square root? I think it was. It was the, yeah, the magnitude. Therefore, the magnitude of I is equal to the square root of 7. 7. So what's the square root of 7? Okay, we have to do square root of 7 like that. It's 2.63. Sorry, 2.65. And then now we've got that, and so now it's going to be 7 divided by 2.65. Let's see if I can make this all a bit smaller. Oh, I can do it here, probably easier. Like that. Yeah. Yeah, and so it's 7 divided by 2.65 is equal to I. 7 divided by the square root of 7 equals 2.65. And now that's squared. So I think I've done something wrong here again, clearly. How do I do that? Power of 2, 7. Ha. So, hang on though. So, the inner product is 7, and then we're doing 7 divided by 2.65. 7 divided by 2.65 is 2.65. 7 divided by square root of 7, and then we square it again. And then it's going to be 7 divided by 7 is 1. Okay, cool, okay, we got it. Good. Yeah, so, and therefore, 1, 1 equals 1, and that's exciting. And uh, I divided by I squared equals 7. Sorry, it equals 7 divided by 2.65 times. Oh, so I just totally lost myself. Damn it. That's so annoying, isn't it, when that happens? Um, so 1 equals 1, but I equals 7, and then I is equal to 2.65 squared. I don't think I actually did that. So the square root of 7 to the power of 2. No. 7. Yes, that's right. Equals that, and then to the power of 2 equals 7. Okay. Good. Okay. Whew. Did that right then. That's good. Um, I wonder if it's worth putting that into GPT. Let's just see what it does, because I'd like it to kind of have this history of this, and then I'll be able to ask the next questions. And then I decided um, I equals 2, yeah, 2 plus I, and therefore uh, I is equal to 2 minus I plus 2 minus I, and therefore and therefore I is equal to 2 plus I 2 minus I plus 2, 4, which equals 2 plus, which equals 4 minus 2I plus 2I plus 1, which equals 3 plus 4, which equals 7. Oh, hang on. Hang on, hang on, hang on. I forgot to do something here. This is wrong. Because I only did it for one, so it's actually supposed to be 7 plus 7 plus 7 plus 7. Whoops, okay. Um, therefore, therefore, this equals 7 plus 7 plus 7 plus 7, which equals 28. 15, 21, 28, yep. So let's start from there, because now it's going to be 28. Oops, equals 7. So 28, so the square root of 28 I guess this doesn't matter actually, I just realised. Anyway, let's just do it. 28, 5.291, and then it's um, 7, it's 28 divided by, yeah, it doesn't matter, of course, 5.292 squared, which of course, you know, undoes that thing, and so you get 1. Okay, fine. Makes sense. Therefore, I equals square root of 28, and therefore equals 28, and so um, I divided by I to the power of 2 is equal to 28 divided by square root of 28 to the power of 2, which equals to 1. Therefore, indeed, 1, 1 is equal to I divided by I to the power of 2, which equals to 1. Let's see what it says anyway. Hopefully didn't lose that. Okay, it didn't. Oh man, something's getting really slow though. Sorry, my mouse is going slow or something. Okay, I think I got it now. You've done a good job working through the idea. Here's a summary and clarification. Given that I and I are linearly independent basis vectors, the goal is to create an orthonormal basis. The first step, as you mentioned, is to normalize the first vector, where I is the magnitude or norm of I. The magnitude of I is defined as I equals the square root of the inner product. You've chosen a sample. The conjugate transpose or the bra of this ket is those. Yes! Now when you complete the inner product, oh, it equals 10. You've mistakenly computed the inner product as if I was a four-dimensional vector. Instead, it's a two-dimensional vector, so you only have two terms in the summation. Sorry, yeah. Thus, I equals 10. The magnitude is 10. When you normalize it, okay, fine. It's this one that I went wrong. So it's going to be 2 times. Oh yeah, that's right. Yeah, yeah. Oh, silly me. This is wrong, but equation still works. 10, etc. Okay, that's fine. We get the point. It's difficult. It's good to work through those because it's real strategy to work through it and kind of convince yourself you're going the right way. And actually, I think it's interesting. I am a programmer, and I suppose in a way I get to test things and get feedback quite quick. And I felt originally like this was quite similar to programming because you get feedback quite quick from the numbers you plug in. But at the same time, it's easy to slip up. Um, at least after having a glass of tequila. So yeah, it's interesting. And Um, you see why people like Albert Einstein, for example, was always mocked because his maths was always wrong, but his ideas were good. Because it's I guess if you're doing lots of these, you're just gonna get a bit lost at some point. So it's easy to make mistakes. Yeah, very interesting. Let's move on. So it says, as for the second vector in the basis, as for the second vector in the basis, consider 2 prime equals II minus 1 II, which is II minus the part pointing along the first unit vector. Think of the arrow example as you read on. Not surprisingly, it is orthogonal to the latter. So 1, 2 prime is equal to, um, let's do that then. So you got 2 prime. I'm not sure what the prime is trying to denote here, but let's ask GPT equals I, which is equals, oh no, sorry, minus, oh, you can't even see this, I'm an idiot. There you go. Minus 1 multiplied by 1 inner product of I, okay, which is equal to 0. So let's imagine 2 prime, well actually let's first ask what the prime is. In the next part, it states a vector called 2. Why are they referring to as 2 prime? What's the significance of this? The use of prime is common. Oh, excuse me. The use of prime is common in mathematics and physics to denote a distinction from the original or to indicate an intermediate step or modified version of an entity. It doesn't necessarily imply a derivative or a particular operation, but rather a variation. In the context of constructing an orthonormal basis using the Gram-Schmidt process, the notation 2 is typically used to denote a version of II that's orthogonal to 1, but not yet normalized. The process of Gram-Schmidt orthogonalization involves iteratively subtracting off projections onto already normalized vectors. So 2 prime is orthogonal to 1 but may not have a magnitude of 1. Once 2 prime is found, it can be normalized to get 2. So in simple terms, 2 prime is orthogonal to 1, 2 is a normalized version of 2 prime and will be orthogonal to 1 with a magnitude of 1. The prime notation simply helps to keep track of intermediate, not yet normalized vectors in the Gram-Schmidt process. Okay, cool. Be right back, I'm going to get another drink. Alright, cool. Let's do this then. So, let's imagine 2 prime is... now it said it wasn't normalized, but I don't think we've been treating any of these as normalized. It doesn't really matter when you're trying to feed in stuff. Let me just take this beer back off. And so, let's just do the same. Well, okay. Maybe let's just do a different one just to test our wits. Let's do 3 plus 2i. Why not? 3 plus I. Okay. And then I. Now this is interesting. And why do you think I is used rather than just another letter? Like, it's kind of annoying. Let's see what it says. Oh man, my mouse is getting owned. I'm not sure what's going on here. The notation of II rather than, say, J or some other letter can indeed seem a bit cumbersome. However, there's a reason behind the choice in many texts. In the context of quantum mechanics and linear algebra, the notation I, etc. is often used to denote a sequence or a set of states, vectors. It can be particularly useful in distinguishing ordered sets of states, where the order or relationship between states is important. Here are a few reasons why authors might opt for this kind of notation. Sequential indication. It clearly indicates a sequence. Is the first state, is the second, is the third, and so on. Avoids confusion. Using different letters might suggest that these states are categorically different or unrelated, rather than part of a sequence or set. Okay. Convention. In certain contexts, especially in quantum mechanics, this type of notation is traditional and has been adopted by many authors. Why I order? Once a convention becomes widespread, it's often maintained for the sake of consistency across literature. Literature. If one starts with A, B, etc., they might run out of letters quickly, especially in systems with many states. The I notation can be extended indefinitely. That being said, it's understandable to find this notation a bit awkward, especially when trying to speak it aloud or differentiate visually between multiple I's. Different texts have different conventions, and while some might stick to this notation for the reasons listed, but others might indeed use different, potentially more intuitive notations. As always, in mathematical notation, the key is consistency and clarity. Yeah, fine. We're fine, it's all good. Let's do, let's do, oh, let's just do an I, and then, well, let's do 0 plus I, and then, I know, 5I, and then, now we have a problem, because this is 2, so this is not going to be right. Let's just be absolutely clear here. This is a basis, so let's do let's do 0, 1, and let me just grab this down. 1 equals 1, 0. Yes, that's better. Good. So it's saying that this equals 2. So first things first, let's minus this one. So I minus 1 is equal to 0 plus I actually I don't know how to subtract vectors. How do you subtract two vectors? Imagine 1 equals 2, 1, 0, I equals 0 plus I, 5I, I minus 1 equals, I'm guessing you just subtract each part, but subtracting two vectors is straightforward. You subtract the corresponding components of the two vectors. Okay, cool. So it's 0 plus I minus 1. You do plus 0 plus I, so it's 0 plus I minus 1 for the second, 5, thus. Oh, okay, you just do it, I see. So, which equals, that's not very clear, is it? 1, 0 plus I minus 1, and then 5I, 5I minus 0, which is going to equal 0 plus I is I minus 1, and then, or minus 1I, I minus 1, no, 1, let's just do the I minus 1, so I don't get confused. And then 5I minus 0 is 5I. Good. So let's see if I got that right. Thus, it's 1, minus 1 plus I. Ah, yeah, okay. Good. I like that. I like that. I like that. I like that. Minus 1. Well, actually, let me undo that. Which equals minus 1 plus I. Yes. I like this. I like this a lot. And then we've got the next part. This is all multiplied by. So let's call this. Oh, okay, that's fine. So minus 1. Let's do this is this. And then the inner product. So it's going to be um, 1 times 1 times 0 plus I plus 1 times 0 plus I plus 0 times 5I. And that is 1 let me just do this like that. I equals that, which equals 1I plus 5. Actually, 0 times 5I is 0, so it's just nothing. So it's just I, which equals I. Cool. Good. And so that is that part. I think I must have got something wrong here because Uh, because this is imaginary. Uh, yeah. So if we were to do this now, it's it's gonna be. Oh, okay. That's fine. So let's do this is a different color. Blue. Let's do these together. And so this will be um, minus 1 plus I squared. So minus 1 plus I squared. And then 5I squared, which equals minus 1 times minus 1 is 1. And then 5 times minus 1 is negative 5. Hmm. So this, I've gone wrong somewhere. So let's go back through, I guess, and also I'll have a sip of my coffee. So up to this point, um, here we were good because we got minus 1 plus I and then 5I. So the 1I is probably the one that's wrong, and I wonder if I misunderstood what it was saying last time about you just have the two components. So let's go back up here. Um, you mistakenly computed the inner product as if I was a four-dimensional vector. Yeah, you just have to do it twice, and that makes sense to me. So, okay. But the inner product was because one, what did I make one? Made one equal that. Um, and so, oh, that's interesting. So, in this case, I did multiply each component. So maybe I should remind myself. Um, can you remind me how to do the inner product again? Is it that you multiply um, because we got to like imagine 1 equals 1 0 and 2 yeah and 2 equals 0, 1. The inner product of these would be, actually let's do AB here, a bit easier. CD, inner product would be A times C plus A times D plus B times C plus D plus B times D, right? A times C plus A times D plus D plus B times C plus B times D. I think the computer's slowing down because this the history of this chat is just too big now. I think that's the problem. No, that's not the correct way to compute the inner product of these vectors. The inner product is given by the conjugate. No, times. A times C plus B times D. Okay, so so this is wrong as well. This last one is wrong, which is really good. I'm glad we're doing this again. Um, wrong. So if we focus back on this, I think I've actually done it right this time. Because I'm just doing it with the one component, right? Around this area, I'm doing it with the wrong component. So 1 times I is I, plus 0 times 5i is 0. So you're left with I. And now the blue is minus 1. Okay, how about multiplying vectors? Is that like what I said? Because that might be the difference there. Well, I suppose I mean um, minus I plus 1, 5i, and that's going to equal II minus 1. And we want to... but hang on. Subtraction happens last, so it's actually... I've done this wrong. BODMAS, baby! That's where I've gone wrong. Okay, fine. So I've gone wrong because I was supposed to multiply these first, right? Multiplication and then subtraction. Come on, kids, it's not that hard. Let's just eradicate this shit then. That's so funny. That is such a noob mistake. Oh my god. Oh man, I love it. I love it really. So let's eradicate this. That's so funny. At least we know what this one is, the red, right? Already know that. So we need to work out 1 times that now. Um, let's see. Uh, don't think I need this either. Well, let's just keep it there. Sorry. I need to not do this one yet. That's what went wrong. So instead, I need to do this. I love the fact that I fell for that. Oh man, that is so funny. So let's start with the red first. Like this. And then let's go for the green. So 1, 1, I is equal to um, oh, it's just one of that. No, it's I of that. So it's essentially 1, 0, I, which is 1, 1, I. Well, let's just do it properly. It's going to be 1 times I, and then 0 times I, which equals I and then 0. Okay, and then you can't quite see this. Gone off the screen a bit. My apologies. So that is now the green part, and then I need to do the negation part. Idiot me. So here's the negation part. I minus I 0 is equal to um, 0 plus I minus I, and then 5I plus minus um, 0, which equals I minus I, 5I minus 0 is 5I, which equals 0, 5I. Well, it says it equals 0. So where did I go wrong with this? If one is 1, 0, then I'm doing 1 times this one is 1 times 0 plus I plus 0 times 5i, yep, which equals I, and then, well, yeah, that's right, I, okay. 1 times 0 plus I. 1 times I is I, plus 0 times 5i is 0, I, must be. And then I'm multiplying that together with that, so 1 is 1 times I, and then 0 times uh, oh god, hang on. I see where I've gone wrong. So let me just check my blood sugars for a second. Ow, it just nearly pulled my sensor off. Yep, we're okay for now. I think I realise where I've gone wrong now. So I've got this thing is correct. Happy with that. And then when I went to multiply it, it's actually, if I just make this super clear, it's actually supposed to just be that really. I. So let's look at this. It's going to be 1 times I, and then 0 times I, which equals I 0. Okay, so that is correct. Okay. And so the last part is the negation of I 0. So I is going to be I was, yeah, 0 plus 1 minus I bod mass. So addition comes first and subtraction, yep, which equals I minus I, which equals 0. And this one is 5i minus 0, which equals 5i, which equals 5i. That does not equal 0. Oh dear. Okay, so let's look back to what we found out before. Okay, I did the next part where it states 1, 2 prime is equal to 1 II minus 1, 1, 1 II equals 0. I took the following assumptions. 1 equals 1, 0. Oh, sorry. I plugged in the following values. 1 equals that. II equals 0 plus I, 5i. Therefore, 1, so therefore, 1 II is equal to 1, 0 plus I plus 0, 5i, which is equal to I. Therefore, and um, 1 multiplied by I, or let's just do this, equals 1 multiplied by I is equal to, well, let's just do the whole thing here. That well, actually, it's equal to 1 times I, 0 times I is equal to I 0. Therefore, I minus I 0 is equal to 0 plus I minus I, and then 5I minus 0 is equal to I minus I, 5I, which is equal to 0, 5I. I must have gone wrong somewhere. Let's step through the problem again and see if we can clearly clarify the procedure. You have asked to compute one, oh, yeah, and I've totally forgot that as well. It's actually one that. Oh, what am I doing here? I've completely, look, I'm going mad. Where did I get that from? I'm going completely mad. I must have mixed two of these together. Oh dear, oh dear. Right, that's silly of me. I can't believe I've just done that. 2 equals. Oh no, here it is, here it is. So 2 equals that. It doesn't equal 0. Oh, okay. That was silly of me. Yeah, I'm too tired, clearly. Um, Fun anyway, I suppose, to see that I'm wrong, right? So I've done a problem calculation wrong. It's good to see these things. I'm just going to assume the next bits are right, because I cannot be going bothered to go through that again. Though it's clear in my head now where I went wrong, and clearly it says that. So let's imagine we get the fascination that we've done it right, which is I minus the part pointing along the first unit vector. Think of the arrow example as you read on. Not surprisingly, it is orthogonal to the latter. We now divide 2 by its norm to get 2, which will be orthogonal to the first and normalized to unity. Finally, consider 3. Uh, 3 minus 1, 1, 3, minus 2, 2, 3, which is orthogonal to both 1 and 2. Dividing by its norm, we get 3, the third member of the orthogonal basis. There is nothing new with the generation of the rest of the basis. Where did we use the linear independence of the original basis? What if we had started with the linearly dependent basis? Then at some point a vector like 2 or 3 would have vanished, putting a stop to the whole procedure. On the other hand, linear independence will assure us that such a thing will never happen since it amounts to having a non-trivial linear combination of linearly independent vectors that adds up the null vector. Go back to the equations for 2 or 3 and satisfy yourself that these are linear combinations of the old basis vectors, and then you've got an exercise. Okay. Well, I think what I'll do then is I might come back to this a little bit. I feel a bit tired because now I've just done all that stuff. Um, I mean that was just silly. So uh, let's just check this exercise out though. So it says form an orthogonal basis in 2 dimensions, starting with a vector equals 3, oh, a hat equals 3i hat plus 4j hat, and b equals. Can you generate another orthonormal basis starting with these 2 vectors? If so, produce another. Yeah, so let's do that later. Um, it was fun anyway to just absolutely see I'm an idiot. I bet the next person who watches this is like. Anyway, thanks for watching, and